Please allow me to introduce our first speaker, Warren Ormsby, who headed up the state GIS theme of the AGP. Warren's career has given him a wealth of experience in petroleum and in the mineral exploration and mining. He is currently Manager of Minerals Geoscience.
Thank you, Charlotte. I was the theme leader for this particular project, this year-long project, and up front, I want to acknowledge the fact that this isn't all my work. It's actually the work of at least 45 people, and they are all duly acknowledged as authors in the AGP Extended Abstract volume. Okay, so we created new spatial data sets for geochronology, isotopes, new geophysical images, and new regolith mapping. We used this information and other information to help gain a better understanding of the crustal architecture. And we did this particularly by mapping major crustal boundaries, both in 2 dimensions and in 3 dimensions. We got more of an insight into mineralisation controls. We did this by selectively extracting data from our different data sets, specifically selected mineralisation sites for various commodities, and again, abandoned gold mine data. We also, for the first time, tapped into our vast geochemical data that we have from exploration industry in our WAMEX data sets. And we combined all this. At the end of this talk, I'll show you how we can combine some of these data sets to hopefully gain some new insights into how you can use this data to help with mineral exploration. These are the first isotope maps ever published by the Geological Survey. They are for neodymium, hafnium, and oxygen. Mapping and associated data sets included the results of new analyses, particularly in the southwest Yilgarn region. These maps can be used to help understand the evolution of the lithosphere over time. So, for example, we use the neodymium and hafnium mapping to identify a similar isotopic composition for the basement beneath the Canning Basin. And this showed similarities to the signatures in the Musgraves, Madura province, and the Kumpana province. And those areas are shown in yellow and green on those images. Now, these suggest actually the existence of a subsurface Proterozoic terrain in between the West Australian craton and the North Australian craton. This interpretation is supported by oxygen isotopic mapping, which reveals a distinction between the Archean cratons and the Proterozoic origins. So you'll see the Proterozoic origins have the higher values shown in blue, those blue circles. Now, we believe these elevated values are due to the reworking of upper crustal material that has been subjected to weathering or low temperature hydrothermal alteration. The oxygen isotope data was also used. It's going to show that this oxygen isotope data was also used to help shed new light on the origins of the Earth's earliest crust. And this information was published in a very recent edition of Nature. So to facilitate further studies, we've made available geochronology sample locations and associated data in the McNaughton Legacy Shrimp Mount collection. Okay, now the normal magnetic and gravity images that you're used to seeing from us, they were updated with new data in 2020. And we also used them to generate multi-scale edges, and otherwise called worms. And I'll come back to them later. Now, we created two new images, the isostatic residual gravity image. In this case, we took the GA MOHO data and used that to make the isostatic correction to the Bouguer gravity image, the new one, that is. We also wanted to look a bit deeper with the aeromagnetic data, so we created this 10-kilometre upward continuation image of the aeromagnetic data to just remove some of that near-surface noise and look a bit deeper down. In a separate and parallel exercise, we made our own depth contour map of the MOHO. We used deep crustal seismic reflection and refraction lines, as well as passive seismic to do this. Now, an important output from this work was our mapping of the major crustal boundaries. Again, this is the first time that we've done this for the entire state. We defined a major crustal boundary as a lithospheric scale structure that's interpreted to transect the MOHO and/or a structure within the crust that forms a boundary between interpreted tectonic units at the terrain or province scale. Now, what we did here is we brought together information not only from the isotopic and geophysical data, but also tapped into the expertise right across the Geological Survey to help define these particular boundaries. We drew upon deep seismic reflection data, and importantly, we integrated it not only in 2D, but integrated it in 3D to create a 3D geo model. And this ensured that we had internal consistency. So the 3D model integrated the 2D mapping with deep-looking passive seismic and also metatelluric profile data. This helped us we helped to identify a new crustal structure in the southwest Yilgarn, but also you'll see some new structures in northeast trending structures in the Pilbara. This exercise also highlighted the complicated architecture in the joining area between the West Australian, North Australian and South Australian cratons. For the first time, the GSWA has harmonised our vast industry geochemical data sets into flat tables using a common set of units. Now, we fully acknowledge that this process is problematic and incomplete, but it did allow us for the first time to really tap into that data that has been locked up in individual reports for so many years. Probably the main issue we got in harmonising the data was we found that some of the data was recorded digitally in the incorrect units. And this, of course, caused a lot of problems when we were trying to convert them to a common set. Nevertheless, we managed to filter out many of the incorrect data and process them in a way that smoothed the results so they could be visualised at different scales to help exploration. So we found the 7 most commonly analysed elements. We imaged up, we processed the data for maximum grade in hole and for mean soil grade. Now, there were over 1 million drill holes in this data set, even filtered, and 3.3 million soil samples. We found pseudocolour drapes to be an effective way to visualise mineralisation trends. And in this example, the maximum grade gold in hole is shown in colour, draped over a hill-shaded image depicting the number of mineralised drill holes for gold. So, whilst this tends to generalise and exaggerate the spatial extent of the gold mineralisation, It's also a powerful tool for visualising mineralisation trends at the relevant scale, because we did this not only at 5 kilometre cell size, which is what you can see here, but we also did it at 300 metre cell size and 100 metre cell size for the drill hole data. What we found here was really quite a remarkable correlation between the mapped major crustal boundaries and many of these regional gold mineralisation trends. Now, from a regional scale to a much more detailed scale, we took the inventory of abandoned mine sites, which has actually been around for over a decade now, and we filtered the data from there to just select those gold workings that could be associated with mineralisation. So we filtered out irrelevant things like rubbish dumps and waste rock dumps, things like that. So then we took those gold workings and we subdivided them into both alluvial or bedrock gold workings. So in this example, which is about 5 k's south of Ormsby, initially I show all of the abandoned mine features that we mapped. We then, if we overlay that with the alluvial gold workings, which are shown in colour, these are coloured up according to depth. And what we did with all this data is we actually processed it in a very similar way to what we did with the drill holes. So in this case, we actually used a 10 metre cell size. So what you can see here is a drape of the maximum depth for gold workings in bedrock gold, overlying a density hill-shaded image of the density of workings. So what you can see then is that we know there's a correlation between maximum working depth and an indication of past production. So what we can see here is a north-south trend, which is probably controlling the bedrock gold mineralisation. And of course, the alluvial workings, the alluvial mineralisation is coming off in an east-west trend, probably from that same source. Now, at a different scale, this is in the Coolgardie-Kalgoorlie area, look at the regolith regimes mapping. So what we did here is we compiled all the regolith mapping into a seamless digital data set, and we just subdivided it into 3 units: depositional, residual, and exposed, or in other words, outcrop. So the outcrop areas are shown here in grey. Overlying that, I show the mineralised drill holes imaged up at a 300 metre cell size. So you can start to see where the gold mineralisation is outcropping and where it is undercover. Added to that is the soil data that's been imaged up in the same manner. So you can start to see the mineralisation trends for gold coming out in this. Also, as part of the AGP, we selected mineralisation sites, in this case for gold. So a bit like the abandoned mines, we filtered out all of the irrelevant data. So we've filtered out processing plants, tailings dams, things like that. So what you see in those yellow dots is known gold mineralisation locations. So if you put them together, you get quite a complete picture of where the mineralisation actually is. And when you look at the Paleo Valley over the top, you can see where the bedrock gold mineralisation may be concealed by these younger sediments, but also remember that we know that there's alluvial gold mineralisation in those paleo channels in its own right. So there are also more opportunities in those channels themselves. Okay, so finally I'm going to show you some examples of how we can combine the data sets at a regional scale to get some indication of what the controls on mineralisation may be. So in this example, I show the hafnium crustal residence time, and I've overlain it with the deepest looking magnetic worms. And I've used both of those combined to interpret that northeast trending structure. Also note that there's a partial correlation between these two very different data sets. If we add the deeper looking gravity worms, we get a more complete picture. You'll see on the bottom right-hand side, very prominent worms associated with the edge of the Fraser zone, so in the Albany-Fraser origin. But you'll also notice that the deeper magnetic worms are running roughly parallel. But elsewhere, many of the gravity worms cross the magnetic worms. As for the magnetics, the gravity does show some correlation, perhaps a poorer one, with the isotopic mapping. Anyway, we removed the isotopic underlay there, and what I'm showing here is a composite image of all of the mineralised drill holes for the 7 commodities that we compiled this mapping for. So this is a way of visualising overall mineralisation trends at a grand scale. And what we can see here is that they don't only correlate with the major crustal boundaries, but also there's a pretty good association with that northeast structural trend. And also, when you look closer, there's actually some associations with the individual deeper looking worms. And I'll draw your attention to the Golden Mile and Kundana area there, where there's a sort of an east-west trending, potentially south-dipping structure indicated by those deep gravity worms. And I wonder if it's any coincidence that we seem to have a similar situation over at Boddington. Also, I draw your attention to the fact that Agnew is at the intersection of a major crustal boundary at this scale and a gravity worm, as is Granny Smith, Gwalia. Also, Gruyere, Gardenwell and Tropicana are all located close to intersections between the deeper magnetic worms and the major crustal boundaries. Okay, now just to show that this approach is also useful for the other minor commodities, what I've overlain here are the selective mineralisation sites for lithium on top of that same image for the composite drill holes for those other major commodities. And again, you'll see that there seems to be some association with that northeast trending structure, and also with the major crustal boundaries and some of the worms. And pretty much all of those are also associated with mineralisation on the regional scale for those other elements. So, in conclusion, the AGP state GIS layers provide key information for investigating and understanding the state's geology. They provide insights into the potential for new discoveries at the statewide, regional and district scale, especially for areas undercover. Thank you.